Right now, wound around a spool the width of a soda can, there's a strip of woven nylon that has already decided, without asking you, whether you live or die in the next tenth of a second. You've pulled that belt across your chest 1,000 times and felt it glide out smooth and easy, then click into place and just sit there, loose enough to breathe, loose enough to lean forward and grab your coffee off the dashboard. But the second your car's speed changes faster than your body expects, that same strip of fabric turns into something closer to a steel bar bolted to the frame. It happens before your foot even finishes stomping the brake. And the strange part is, nothing about the belt itself changes. What changes is a steel ball the size of a marble, sitting inside a little plastic cup, deciding that gravity just stopped being the boss. Start with the boring version, the one that runs every single day and never gets any credit. Inside the plastic housing bolted near your hip, there's a spool, and wound around that spool is your belt, and behind that spool is a coiled metal spring, the same basic idea as an old wind-up clock. Pull the belt out, and you're stretching that spring tighter. Let go, and the spring wants to snap back to its resting shape, so it reels the slack belt back in. That's why a seatbelt never just falls in your lap in a pile of loose fabric. It's under constant, gentle tension, always trying to tidy itself up. This part of the system has one job, and one job only: take up slack. It is not, on its own, capable of stopping you from flying through a windshield. If the spool could spin freely forever, no matter how hard you yanked on that belt, it would just keep feeding out fabric, and in a real crash, you'd sail forward with the belt uselessly unspooling behind you. So somewhere in that housing, something has to know the difference between you casually reaching for your coffee and your entire vehicle trying to stop from 60 miles an hour to 0 in about a second and a half. That something is a locking mechanism, and it has not one but two completely separate ways of catching you. The first one lives outside the belt entirely. It doesn't care how fast you're pulling the strap. It cares about the car. Picture a small chamber, sometimes shaped like a bowl, sometimes a little ramp, with a dense steel ball resting at the bottom of it, held there purely by gravity. As long as your car is moving in a straight line at a steady speed, or even accelerating and braking gently, that ball just sits in its little dip, minding its own business. But slam the brakes, and the car's body suddenly decelerates hard, while the ball, obeying a rule the car can't override, tries to keep moving forward at the speed it was already going. From the ball's point of view, it's not doing anything unusual. It's the car that's suddenly lurching backward relative to it. That relative motion sends the ball rolling up the ramp, and the ramp is shaped so that as the ball climbs, it lifts a tiny pivoting arm above it. That arm is connected to a hooked piece of metal called a pawl, and lifting the arm swings the pawl directly into the teeth of a ratchet gear fixed to the end of the spool. The instant those teeth catch, the spool cannot spin forward anymore. The belt stops feeding out. You are, in that same instant, locked to the frame of your car. This whole trick is called vehicle sensing, because the sensor is responding to what the vehicle is doing, not what you're doing with the strap. And underneath it is one of the oldest and simplest ideas in physics. An object in motion stays in motion unless something forces it to change. A principle Isaac Newton wrote down more than 300 years ago, and which every single seatbelt on Earth quietly depends on every single day. Your body wants to keep traveling at 60 miles an hour even after the car has stopped. So does that steel ball. The only difference is the ball's resistance to stopping is what triggers the mechanism that then stops you. But what if a car only ever had that one sensor and nothing else? Here's the gap it leaves open. Imagine you're sitting still, parked, seatbelt on, and you suddenly yank the strap hard and fast, the way you might if you were trying to reach something behind the seat in a hurry. The car itself hasn't decelerated at all. It's sitting perfectly still. That little steel ball has no reason to roll anywhere, because nothing about the vehicle's motion has changed. If vehicle sensing were the only system in play, a hard, sudden pull on the webbing itself would do nothing, and the belt would just keep feeding out exactly like it does when you calmly lean forward. That's a real problem, because in some crash scenarios, especially a rollover or a secondary impact after the first one, the fastest, most violent motion is happening to your body relative to the belt, not necessarily to the whole car relative to the road at that exact moment. So engineers built a second, completely independent trigger, one that watches the spool itself instead of the car. This second system is called webbing sensing, and it lives right on the spool axle. Attached to the spool is a small centrifugal clutch, essentially a tiny weighted lever sitting close to the spool's center, held there by a light spring. Under normal gentle belt movement, the spool spins slowly enough that this little weight just sits put, tucked in close. But yank the belt hard and fast, the kind of violent pull that happens when your torso suddenly lurches forward in an impact, and the spool itself spins up to a much higher rotational speed in a fraction of a second. That fast spin flings the little weight outward, the exact same physics that presses you into the door of a car taking a sharp turn, and once that weight swings far enough out, it catches on a fixed ring of teeth built into the housing around the spool. Not the belt this time, but the spinning part itself. The moment it catches, the spool's rotation is arrested almost instantly, and again, the belt stops paying out. So you actually have two independent tripwires working in parallel at all times, one watching the car's deceleration through gravity and inertia, acting on a free-rolling ball, and one watching the spool's own rotational speed through centrifugal force, acting on a weighted lever. Either one alone can lock the belt. Together, they cover nearly every way a crash can actually unfold, whether the violence starts with the car or starts with your body. Here's a detour worth taking, because it explains something people rarely think about. What if engineers had built a belt that locked permanently, all the time, the second you sat down, so there was zero play whatsoever? You'd think that sounds safer. It isn't. And the reason comes down to something called locking sensitivity. A belt that's rigid all the time would fight you on every normal movement, every reach for the radio, every twist to grab a bag from the back seat, and drivers being drivers, a huge number of people would simply stop wearing it, or wear it loosely across their stomach to get some slack, which is arguably more dangerous than no belt at all in some crash geometries. The entire design philosophy of these two sensors is to stay completely invisible during ordinary driving, and slam shut only in the narrow window of time, where the physics says something has gone seriously wrong. That balance between everyday comfort and split-second rigidity is the whole engineering puzzle, and it's why the mechanism has two separate triggers rather than one blunt one. Now, the moment the pawl catches the ratchet teeth, whichever sensor triggered it, something interesting happens that most people never notice, because it happens in milliseconds, and it's designed specifically not to be noticed. The spool doesn't actually stop dead like a brick wall. If it did, a person traveling at highway speed would go from moving to completely stationary at the chest in an instant, and the forces involved would crack ribs, or worse, tear the aorta clean through. So running down the center of that spool, hidden from view, is a thin rod of specially hardened steel called a torsion bar. One end of the torsion bar is locked rigidly by the pawl and ratchet. The other end is fixed to the belt spool itself. When the crash forces slam your body forward against the locked belt, instead of the whole spool being frozen solid, that inner rod twists, like wringing out a small towel, allowing a few carefully calculated inches of belt to feed out in a slow, controlled, resisted way, even though the outer teeth are completely locked. This is a direct application of Hooke's law, the principle that a material resists deformation with a force proportional to how far you bend or twist it, first worked out by the English scientist Robert Hooke in the 1600s while he was studying springs. The torsion bar is essentially a very stiff, very precisely engineered spring, acting as a shock absorber for your chest, spreading the stopping force out over a slightly longer span of time, instead of delivering it all in one brutal instant. And here's another branch worth stepping into, because it changes how you should think about what a seatbelt is actually for. What if the belt were made of something with zero stretch at all, like a steel cable instead of woven nylon? You might assume less stretch means more safety, since it would keep you pinned more rigidly in place. In reality, engineers deliberately choose webbing material with a specific, measured amount of elasticity, because a small controlled stretch, combined with the torsion bar's controlled twist, is what keeps the deceleration forces on your ribcage and pelvis below the threshold that causes serious internal injury. A completely rigid restraint would stop your skeleton instantly, while your internal organs, still obeying that same law of inertia, kept slamming forward inside your body. The goal was never to stop you as fast as physically possible. It was always to stop you as gently as the available distance and time would allow, which is a very different design target, and one that took decades of crash testing to get right. Even the material of the strap itself was never a casual choice. Early seatbelts were woven from cotton or nylon in loose weaves borrowed straight from parachute harnesses, and it turned out parachute webbing was actually too elastic for the job, stretching so much under load that a wearer could still travel a dangerous distance forward before the material took up the force. Modern belts use a tightly woven polyester webbing instead, chosen specifically because polyester fibers stretch less than nylon under sustained load and resist sagging over years of sun exposure and humidity sitting in a parked car. The weave pattern itself, usually a tight twill, is engineered so that under a sudden violent load, the individual fibers grip against each other and spread tension evenly across the full width of the strap, rather than concentrating it at one thread, which is exactly why a seatbelt, several centimeters wide, feels almost rigid in a crash, despite being made of the same basic fiber family as a t-shirt. Combine that calibrated low-stretch weave with the torsion bar's controlled twist deeper inside the retractor, and you get two layers of engineered give working together, one in the fabric itself, one hidden in the steel rod behind it, each tuned to bleed off energy at a different rate. Long before any of this existed in a mass-produced car, restraint systems were a mess. Early lap belts, the kind found in cars through the 1950s, held your hips in place but did nothing for your upper body, meaning in a serious frontal crash your torso and head would fold forward like a hinge, right into the steering wheel or dashboard. The engineer who fixed this was a Swedish aviation specialist named Niels Bolin, who had spent years designing ejector seat systems for fighter pilots, where getting a harness to hold a human body under violent, sudden forces was literally a matter of pilots surviving being blasted out of a cockpit. In 1958, Volvo hired him specifically to bring that expertise into cars. And within a year, he had designed the three-point belt, the diagonal shoulder strap, combined with the lap strap in a single Y-shaped piece of webbing anchored at 3 points around the body. What makes his story stick is a fairly remarkable decision Volvo made right alongside the invention. Rather than patenting it for exclusive profit, the company released the design freely to every other car manufacturer on Earth, on the reasoning that a safety feature that only saves Volvo drivers isn't nearly as valuable as one that saves everyone. It's one of the very few major automotive inventions in history where the company chose global adoption over exclusive ownership, and it's a large part of why nearly every seatbelt on the planet today still uses that same basic three-point geometry Bolin sketched out more than 60 years ago. But locking the belt and controlling its stretch only handles the crash once it's already fully underway. There's a piece of this system that acts before the worst of the impact even arrives, and it's arguably the most dramatic component in the entire chain. It's called a pretensioner, and it exists to solve a very specific, very sneaky problem: slack. Even with a belt buckled snugly, there's almost always a small amount of give, whether from thick winter clothing, from the webbing settling, or simply from the natural give built into any woven material. In the opening milliseconds of a serious frontal collision, before the main crash forces even peak, that tiny bit of slack means your body can drift forward slightly before the belt truly bites. A few extra centimeters of forward travel sounds trivial, but at highway speed, in the split second before your head might reach an airbag or a dashboard, it matters enormously. To eliminate that gap, the pretensioner uses what is essentially a small, precisely engineered explosive. Sitting near the base of the seatbelt spool is a sealed cylinder containing a pyrotechnic charge, a chemical propellant almost identical in principle to what's inside an airbag inflator. The moment a crash sensor detects a collision severe enough to warrant it, the car's computer sends an electrical signal that ignites that charge in a fraction of a second. The rapidly expanding gas from that tiny controlled explosion drives a piston violently along a small-toothed rack, and that rack is mechanically linked to the spool, forcing it to spin backward and yank the belt taut against your body almost instantaneously, removing the slack before the main impact forces have even had time to build. It's over and spent within about 15 to 20 milliseconds, faster than you can consciously register that anything happened at all, and by the time your body actually starts loading force into the belt, there is no gap left to close. Companies like Autoliv, TRW, and Bosch are the names behind a huge share of the pretensioner and retractor units built into cars sold worldwide, and their engineering teams spend enormous effort tuning exactly how much force that little explosive charge delivers. Because too weak and it fails to remove the slack in time, too strong and it can cause its own bruising by yanking the belt too hard against a body that hasn't even begun decelerating yet. It's a genuinely strange kind of engineering, deliberately setting off a small explosion inches from a person's chest, precisely calibrated to protect them rather than harm them. Behind that decision to fire sits a piece of electronics working on a completely different timescale than the mechanical ball and pawl. Bolted to the car's frame, usually somewhere near the center console, is a small accelerometer, a chip that measures how quickly the car's velocity is changing along each axis. The same basic sensing technology that lets a smartphone know which way is up. During a crash, that chip is sampling deceleration thousands of times per second, and the moment the reading crosses a threshold that the manufacturer's engineers have determined, through years of physical crash testing, corresponds to a genuinely dangerous impact rather than a hard pothole or an aggressive stop, the car's restraint control computer fires the pretensioner's igniter within a few milliseconds. This is the one part of the whole story where the belt's behavior depends on electricity and a microchip rather than pure mechanics, and it's specifically layered on top of the purely mechanical ball and pawl system rather than replacing it, precisely because a fully electronic system depends on power, wiring, and a working computer, all of which can, in rare cases, be damaged in the earliest fraction of a crash itself. The mechanical locking system needs none of that. It works with a dead battery, a severed wire, or a computer that's already failed, because gravity and rotating mass don't need a power supply. What if a car relied only on that electronic accelerometer and skipped the mechanical ball and pawl entirely? On paper, it sounds more precise, since a chip can measure deceleration far more finely than a rolling steel ball ever could. But it introduces a single point of failure that engineers have spent decades trying to avoid in safety-critical systems. Wiring can corrode, connectors can loosen, a computer can crash or lose power in exactly the violent, chaotic first instant of an impact when it's needed most. A steel ball sitting in a bowl, by contrast, cannot lose power, cannot glitch, and cannot be disabled by a blown fuse. That's precisely why the belt lock itself has stayed almost entirely mechanical for more than 60 years, even as the rest of the car has filled up with sensors and computers, while the electronic side has only ever been added as a second, faster-acting layer specifically for the pretensioner, never as a replacement for the core locking function. What if the pretensioner fired, but the torsion bar didn't exist, so the belt simply locked rock solid the instant the slack was removed? You'd actually be trading one danger for another. The pretensioner's whole purpose is to close the gap before the crash forces peak, but the torsion bar's job is to manage what happens after that, letting a small, controlled amount of belt feed back out as the true crash forces slam through. Without that controlled give, all the benefit of removing the slack early would be undone by delivering the stopping force in one uncontrolled jolt, instead of a spread-out, cushioned one. The two systems are built to work in sequence, one closing the gap, the other absorbing the shock, and neither one alone does the whole job. Before getting to that refinement, it's worth pausing on a mode most drivers have stumbled into by accident without ever knowing its name. Pull a seatbelt all the way out to its full length, and you'll notice it suddenly behaves differently, ratcheting in one direction only, clicking tighter each time you pull it back in, but refusing to feed any slack back out no matter how gently you tug. That's called automatic locking mode, and it's a deliberate second personality built into the same spool, switched on by a completely different set of teeth that only engage once the belt has been drawn out to its maximum length. Parents use this constantly without necessarily knowing the mechanism behind it, because it's exactly what's needed to cinch a child car seat down tight and keep it from shifting, something the normal free-spooling mode, built for comfort during ordinary driving, would never allow. Pull the belt out fully, let it ratchet down snug around the car seat's frame, and the spool will only ever tighten further from that point, never loosen, until you let the whole thing retract completely and start over. It's a small design choice, but it shows that the retractor isn't just one switch that's either locked or unlocked. It's a small mechanical decision tree, quietly picking between three states: free spooling for everyday comfort, emergency locking for a crash, and automatic locking for situations where you want rigidity on purpose. There's also a sensor riding along in this system that has nothing to do with stopping your body and everything to do with getting you to put the belt on in the first place. Tucked into the buckle itself is a small switch, nothing more than two metal contacts that touch the instant the tongue clicks into place, closing a simple electrical circuit. Leave that circuit open, meaning the belt is unbuckled, and the car's computer treats it as an ongoing condition worth nagging you about, chiming and flashing a warning light for as long as the seat above it registers weight without a corresponding buckled signal. It's a comparatively simple piece of the puzzle next to a twisting torsion bar or an explosive pretensioner. But it closes an important loop, because every mechanism described so far, the ball, the ratchet, the centrifugal weight, the torsion bar, all of it is completely irrelevant if the buckle was never closed to begin with. That tiny switch is really the gatekeeper for everything else in the chain, even getting a chance to work. There's one more refinement worth mentioning, because it explains why a modern crash doesn't feel quite as violent as the raw numbers would suggest it should. Many retractors include a load limiter built directly into that torsion bar assembly, essentially a rod engineered to twist at a very specific, tested resistance. Engineers tune that resistance using real crash test data and instrumented dummies, adjusting exactly how much force the chest can safely absorb before the bar should start yielding and feeding out those last few inches of webbing. Too stiff and too much force transfers straight into the rib cage. Too soft, and the person travels too far forward before the harness fully arrests their motion, risking contact with the wheel or dashboard, even with the belt locked. Getting that number right, down to fractions of an inch of allowable travel, is one of the quieter but more important pieces of crash safety engineering, and it's constantly being refined as cars get lighter, faster, and packed with more advanced sensors. Trace the whole sequence from the very start, and it's really one continuous handoff. The car begins decelerating violently, or the belt gets yanked with sudden force. Either the steel ball rolling on inertia or the centrifugal weight spinning on the axle catches that change within a few thousandths of a second and throws a mechanical pawl into a ratchet gear. Almost simultaneously, if the crash sensors judge the impact severe enough, a tiny explosive charge fires, yanking out the last bit of slack before the true crash forces even arrive. Then, as your body's own inertia slams forward into the now locked webbing, a thin steel rod inside the spool twists under calculated resistance, feeding out just enough belt to keep the forces on your rib cage below the threshold of serious injury. All while the geometry Nils Bohlin sketched out back in 1959 spreads that load across your shoulder, chest, and hips, instead of concentrating it in one spot. None of it requires a single line of computer code to make the core locking decision. No processor, no software, no battery even, in that most fundamental layer. A steel ball obeying gravity, a weighted lever obeying rotation, and a twisting rod obeying the same elastic principle Robert Hooke described while poking at metal springs 3.5 centuries ago. The explosive charge and the crash sensors are newer additions layered on top, adding speed and precision. But the base mechanism, the part that actually decides in that first instant whether the belt locks or lets you keep leaning forward for your coffee, is almost entirely mechanical, and entirely dependent on the same laws of motion that governed a falling apple in a garden in the 1660s. Every time you climb into a car and click that buckle without a second thought, you're arming a small, silent machine that has already decided, purely through the shape of a ramp and the weight of a marble-sized ball, exactly how it will catch you the instant physics turns against you.